Okay, in this video I'm going to talk about a thing called the cosmic distance ladder, which is the method by which we work out how far away things are via a set of steps on a ladder, and each step depends on the previous step, which is what's known as a ladder. And the ultimate step on the ladder are supernovas. And so we'll get on to supernovas and why some supernovas are standard candles later on in the talk. So you know the first step in measuring distance to stars, it is using parallax. So we can work out the distance using the parallax angle, and this is quite a nice diagram here from Wikipedia. But you can see that really parallax depends on being able to measure them against more distant stars. So parallax can only give us the values for near stars because it's being how the near star moves in its projection against the distant stars. So parallax is quite limited. And of course, parallax has got no way of being able to give us distances to things like galaxies. The size of the parallax angle would just be too tiny to be useful. So parallax is just the first step, although you know, because we've talked about it quite a few times now, that there is this Gaia satellite that is making much more detailed, much more high-spec measurements of parallax to stars, but I think going out at higher distances than we've done before at the moment. This is just an illustration from their very unhelpful set of posters that they have on their website. When I saw they had posters on their website, I thought, oh, that'll be useful. Maybe I'll get one printed and put it up at school. But yeah, no. Right, to get to the next step on our distance ladder, we need what are called standard candles. Now, it seems a stupid idea to discuss standard candles when we're talking about cosmic distances. But of course, if we know how bright a candle should be, and then we have a distant candle, we can work out exactly how distant it is because we can use the inverse square law, because we know how bright it is, we know how bright it should be, and therefore from how far away it is and how bright it looks to us at that distance, we can work the distance out using the inverse square law. So if we can have something that we know what its brightness should be, that then acts as a standard candle for us. And the term comes from the fact that before SI was thoroughly accepted, we really did have a thing called a standard candle. So you know, this is just a straight lift off Wikipedia, but if you have a read of this, you can see that the English standard candle was the light produced by a pure spermaceti candle weighing 1/6 of a pound and burning at a rate of 120 grains an hour, and a grain being a fraction of an ounce. And spermaceti is a wax-like material that surrounds the brain of sperm whales. So not very nice. I have to say, we don't kill sperm whales in order to get standard candles these days. SI has a definition of amounts of light that does not rely on a standard candle. But once upon a time, we relied on standard candles for our definition of how bright something was. And astronomy still does. It's just that the standard candles are stars or supernovas. Now, the main star that is a standard candle is a thing called a Cepheid variable. The archetypal variable star that these are based upon is Delta Cepheus, so the fourth brightest star in the constellation Cepheus. And so Cepheid means pertaining to Cepheus, so Cepheid variables. And there are lots of different sorts of variable stars, but they're the variable star that change with this sawtooth waveform you can see here. And by sawtooth wave, I mean that it's steeper on one side than the other, because that's true of most saws. It's not true of all saws. Both saws aren't steeper than one side than the other, but it's true of most saws that they are steeper on one side than the other. So this kind of shape is known as a sawtooth waveform. We now know that the way that Cepheid variables work is that they've got quite a lot of helium in their mix of their envelope, and helium, like all the other gases, when it's ionized, when it's charged, interacts strongly with photons. And so when the helium has a charge, when it's been ionized, it interacts strongly with the photons, and it gets pushed outwards by radiation pressure. And so the star actually expands because the radiation pressure is high, because all this ionized helium, it only has to be singly ionized, but double ionized as well, helium is being pushed out by the radiation pressure. But of course, as it pushes out, as the outer layer of the star pushes out, it cools. Expanding things always cool. So as the outer layer pushes out, it cools, and it cooling has the result of the helium maybe no longer being ionized. The helium starts to grab itself electrons and no longer be ionized. And of course, when the helium is no longer ionized, the radiation pressure falls because the helium atoms do not interact strongly with the photons. So the radiation pressure falls, which means that the surface of the star contracts back down in again. And of course, as the surface of the star contracts back down again and again, the helium heats up, the helium starts to ionize, the radiation pressure goes back up, the star expands back out again, and so we get the star expanding and contracting and expanding and contracting as the helium is ionized and then becomes an atom again, and then is ionized again, and then becomes an atom again. The star pulses in and out, and it's this pulsing in and out with a change of magnitude of, what's that, 0.5? So what's that? Sort of, I'm not sure how many times that is different in light. What's 2.51 to the power of 0.5? But anyway, you get the idea. These stars are pulsing, and they pulse very regularly. You can see that this one's off a NASA website. You can see that the lifetime of this one, or rather the time period for the pulsing, is 9.048 days. Now, they weren't, Cepheids weren't discovered by Henrietta Swan Leavitt, who was another of the very many women who made important discoveries whilst working for Harvard. The professor at Harvard asked her to investigate the variable stars that were in the Magellanic Clouds. I've mentioned the Magellanic Clouds. They're a dwarf galaxy that's that orbits the Milky Way and are visible from the southern hemisphere. Anyway, he asked her to investigate these variable stars. So she found all the variable stars where she could and made measurements of them in the Magellanic Clouds. And of course, because she's a good physicist, she draws a graph. The graph here, as it tells you, the horizontal axis is the log of the time period. So that time period that was 9.048, whatever it was on the previous page. So she took logs of it because it's clearly going to be something to do with a power law. She took logs of the time, and then the vertical axis is magnitude, with the top line being its brightest magnitude and the bottom line being the stars when it's at the bottom of its brightness peak. And she found this relationship that you can see here, that there is that the log of the time period connects directly to the magnitude of the star. Now, you might be wondering why that's important, or you might have worked out why that's important from this talk of standard candles. But of course, all of these stars that she was working on were in the Magellanic Cloud, and because they were in the Magellanic Cloud, they were all roughly the same distance from us. The distance between us and the Magellanic Cloud is much further than any change in distance within the Magellanic Cloud that might affect our measurements. So they're all effectively the same distance. So this effect that she's finding is a real effect. It depends entirely upon the stars. The brightness of a Cepheid variable can be worked out from its time period. Fantastic. We've got a standard candle. We've got something whose brightness can be worked out from its time period. So all we need is some Cepheid variables that are a bit closer than the Magellanic Clouds, so that we can use the parallax to work out how far they are away. And then once we know how far they are away, we know how far away every other Cepheid variable is providing we can measure that Cepheid variable's time period, because the time period will give its brightness, and then from the brightness we use inverse square rule to work out how far away it must be us regarding it. So Swan-Leavitt finds, with this result, with plotting this graph, finds us a standard candle. And she was actually one of the members of the Nobel Committee attempted to nominate her for the Nobel Prize for this in the 1920s. Unfortunately, she was already dead. I guess back in the 20s, that kind of news didn't travel around the world the way that it does now with social media and things. And so, yeah, I shouldn't laugh. She was already dead at the point when he tried to nominate her, and Nobel Prizes are not awarded posthumously. So, unfortunately for Henrietta, she died a fraction early. But her work was used by Hubble. I think I mentioned this in the lesson. Hubble found Cepheid variables in the nearby spiral galaxies, which at the time were thought to be spiral nebulae. They were thought to be part of our galaxy. But Hubble found the Cepheid variables. He used Swan-Leavitt's formula to work out how bright they must be, and then looked at how bright they actually were, and he realised that they were actually a hell of a lot further away than we thought they were, and that they weren't part of our galaxy at all. They were entirely separate galaxies. So we get the next step in our distance ladder. We've gone from only being able to do stars that are relatively close to us to being able to do the nearby galaxies. If we've got a big enough telescope, this 100-inch hooker that this talks about here was the largest telescope in the world at the time. If we've got a big enough telescope that we can resolve Cepheid variables within a galaxy, we can use the Cepheid variables to work out how far away that galaxy is. And as I said in the lesson, that turns out to be megaparsecs. So up to kiloparsecs for distances across a galaxy. To the distances to the next galaxy, we've moved into megaparsecs. And Hubble made that next step using Swan-Leavitt's work. So here's our distance ladder now. Parallax angle. Parallax angle allows us to work out the distance for the nearest Cepheids, and then once we've got the values for the nearest Cepheids, we can use the inverse square law to work out much more distant Cepheids, including nearby galaxies. And since then, the Hubble Space Telescope was used to isolate Cepheid variables in much further away galaxies. So this cosmic distance ladder was able to be extended by the fact that the Hubble Space Telescope could resolve Cepheids in more distant galaxies, and so get better distances. And of course, now we've got ground-based telescopes that are better than Hubble, and so we can push that a bit further. We can get even more distant galaxies with the Cepheid variables. We still can't get out to massive distances. To get to huge distances that sort of start to take us closer to the start of the universe, because we talked again about in class today about the fact that the further away you look, the further back in time you are looking. So the further away you look at an object, the closer to the start of the universe that object must be in time at the point the light left it to start its long travel to us. So we need something that we can confidently measure at such huge distances. And there's not much you can confidently measure at those kinds of distances. There are quasars that we've just got to mention, and of course there are supernovas. We've mentioned already that there are several different kinds of supernova. Here is Wikipedia's graph of the light curves of the various different supernovas. So we've got absolute magnitude here against days along here, and it's been reset so that they peak at day 0. So that before the peak goes negative, and then after the peak goes positive. And we've got different kinds of supernovas. And here, but the one that we're interested in, the ones that we've talked about before are type 2s. We've talked about core collapse supernovas. Type 2s could be higher in absolute magnitude, lower in absolute magnitude, depends on how big the star is. But the ones that we're interested in today are type 1As. because it turns out that type 1As always have an absolute magnitude peak of minus 19. So how do we know this? Well, of course, we've got distances because of the Cepheids. We've got distances to nearby galaxies. So supernova, a type 1A supernova goes off in that galaxy. We can measure its apparent magnitude. We can use our apparent to absolute magnitude formula because we know the distance to work out what the brightness of the type 1A is. And every type 1A that we measure turns out to be able to have an absolute magnitude of minus 19. Every one we measure. So we can be pretty sure that type 1A supernovas are another standard candle, a hugely brighter standard candle than the Cepheids. So we can use type 1A supernovas to get us to much larger distances because we use the Cepheids to work out the distance to the galaxies. And those distances to those galaxies gave us the distances to the type 1A supernovas. We worked out that the type 1A supernovas always have the same absolute magnitude, and therefore we can then use much more distant type 1A supernovas, know that they're going to have an absolute magnitude from minus 19, measure their apparent magnitude, calculate their distance. So this ladder, each bit of the ladder, depends on the previous one. So we're interested in the site in the black line here. You have to be able to reproduce that black line for your exam. You have to be able to sketch this. So you have to be able to put the right number of days along the bottom, and you have to put the right peak value of minus 19 up the side. So this is a graph that you have to know, that you have to be able to sketch. You do not have to be able to sketch all of the others, just the black line. So it needs to start at 10 days before the peak at 0, at minus 19, and then decay away over the next sort of 80 to 100 days. All right, must be able to reproduce that in the exam. Now, what mechanism could possibly give us supernovas that always went off with exactly the same brightness? It doesn't seem reasonable that supernovas should always go off with exactly the same brightness, because surely the mass of the stars that are supernovaing are going to vary. Well, a mechanism has been worked out. Whether this mechanism is completely right is still open to question, but a mechanism has been suggested, and that mechanism relies on a white dwarf and a red giant binary. And white dwarf and red giant binaries are not unusual things because they're going to be born at about the same time out of the same giant molecular cloud of gas that collapses. They're probably going to be similar sizes, but not exactly the same size. So our pair of binary stars, sun-sized binary stars, roughly the same size, orbiting around each other. But of course, as you remember from that graph right back when we did the lifetime of stars, about the mass of the star compared to its lifetime, the slightly heavier of the two will burn through its hydrogen and therefore become red giant before the other one does. So although they start off as a very, very similar sun-sized stars, just because one's a little bit bigger than the other, one of them will go through its life cycle slightly faster. So one of them will be in its white dwarf stage when the other one has only just reached red giant. Now, as the second one reaches red giant, of course, it's going to swell up. It's going to swell up, but then in orbit pretty close is this really compact high gravity object. And so the consequence of the second star swelling up into its red giant phase is that the second star starts to lose mass down onto the white dwarf. The white dwarf pinches mass from the red giant. The red giant swells up, becomes unstable, and in the process of swelling up and throwing off its outer layers, those outer layers get swallowed up by the white dwarf. And they actually spiral down onto the white dwarf, which is what this diagram here is supposed to be illustrating. And a nova is a lump of material landing on the surface of a white dwarf, and that lump flaring up on the surface of the white dwarf and doing nuclear fusion briefly on the surface of the white dwarf, and that of course flares up the brightness of the white dwarf, but it's not massive and it's only temporary, and so that's a nova. A nova is a lump of this material from our red giant landing on our white dwarf and restarting nuclear fusion briefly on the surface of our white dwarf. But here's the interesting bit. A white dwarf can only reach a certain mass. Once it gets beyond that certain mass, then the method that we said that was holding it up, the electron degeneracy pressure, is not capable of holding it up any further. So there's going to become a point where our white dwarf has accreted so much material from our red giant that the white dwarf becomes too heavy for electron degeneracy pressure to hold it up. And at that moment, it's got to implode. Moment it reaches that mass. And of course, it's the same mass for every white dwarf. It doesn't matter what mass the white dwarf started at, it's going to implode, it's going to supernova at the point when it's gained enough mass from the red giant to reach what's known as the Chandrasekhar limit. And that's because Subramanian Chandrasekhar, an Indian-born physicist, worked out the value that a star could hold up using the electron degeneracy pressure, and he worked it out to be 1.4. I've seen it as 1.44, but when I was looking it up yesterday, I didn't get that value. But I've seen it at 1.4 times the mass of the sun. So you got to imagine it's going to take the white dwarf a little while to get there, because if it was a sun-sized white dwarf, because it's thrown off most of its outer layers, so it's probably ended up the white dwarf bit only being 0.6 of the mass of the sun, because the other 0.4 has been thrown outwards as the planetary nebula. So it's gone down, our white dwarf has gone down to say 0.6 of us, and it's then got to get another 0.8 of a solar mass off its neighbouring red giant in order to get up to the stage where it exceeds the Chandrasekhar limit, and at the moment it exceeds the Chandrasekhar limit, it will implode. Fusion will restart, it'll collapse inwards, presumably becoming a neutron star, and it becomes incredibly bright. And that is believed to be what a type 1a supernova is. The spectroscopy of a type 1a supernova shows a huge quantity of helium, but also shows helium fusing into carbon and oxygen. And that suggests that what's starting is definitely a white dwarf. And so we get white dwarfs go beyond the Chandrasekhar limit and implode. And because they always go at the same moment, they always go when they reach 1.4 solar masses, they're always going to go off with exactly the same brightness, because they're always going off at exactly the same mass. Clever, eh? It's not certain this is definitely what's happening. There's lots of people out there trying to search for these, looking back through their old photos after they see a type 1a. Can you go back through your old images at the same place? Can you see this white dwarf red giant binary? And that question is still open. Is it definitely this is what's going on? But this is the explanation that people can come up with for why type 1a's are always the same brightness. And that's not theory that's saying they're always the same brightness, that's measurement saying that they're always the same brightness, and the theory is having to try and explain why it is that they're always the same brightness. So that covers it. And again, the amount you need to know, quite small. Standard candles allow us to find distances further than those that we can get from parallax. And the most important, most recently discovered things that are standard candles are type 1a supernovas. You've got to be able to draw the light curve of a type 1a supernova, and therefore you've got to remember that they peak at an absolute magnitude of -19. That the peak is 10 days after the start, and that they fade over the next 80 days. That's also that you can sketch the graph, sort of thing. -19 up there. Okay, so that's also that you can sketch that graph. And then the mechanism is probably not all that likely to be asked about, but the mechanism I just think is interesting. That it's why are they always the same brightness? They're always the same brightness because they always reach this Chandrasekhar limit. The electron degeneracy pressure that we talked about is holding white dwarfs up. can't hold them up anymore. Okay, just a short one that, but the distance ladder is important for Hubble's work, which we did in the lesson today. We did the Hubble law. Well, the Hubble law was worked out using the Cepheids as the standard candles, and we're going to go on and talk about the deviations from Hubble's law, and the deviations from Hubble's law were found by using the type 1a supernovas as standard candles.